This next chapter concerns the electric potential and potential energy. The potential and potential energy are two concepts that complement the concept of the vectors of force and the electric field. And this first module just gives us an introduction to these. It's non-mathematical essentially. The potential energy of a system is the work necessary to assemble those charges from infinity. So if I just have one charge, if I just have one charge, a plus charge, and I put it somewhere, it doesn't take any work to do that because it didn't have anything opposing it. But if I try to bring in another plus charge and I drag it in, it's pushing against this one, and so this plus charge has to do work. I have to do work to drag this in to where they are a certain distance apart. And I can ask, how much work does that take? And we're going to calculate that in a few minutes. The potential energy, on the other hand, is a scalar, and it's going to be measured in units of joules, as energy always is. This is kind of like compressing a spring. You recall that when we compressed a spring, we looked at force times distance, and that gave us our total potential energy. And we had to integrate that and add that all up, and that was because the force changed over time. So the potential energy of a spring was equal to the integral of 1/2 kx squared times dx, and we had to, in calculus, perform that integral. Here we have to be a little bit more careful that we're pushing in the direction of the force, because actually this is a dot product. We didn't have to worry about that with our one-dimensional spring. Minus kx, pardon me. So that our spring was a force of kx, and we multiplied that by a distance, dx, and integrated that. And this, of course, gave us our 1/2 kx squared when we brought the constant k outside of the integral and integrated x dx. Okay, we have to do the same kind of thing here in the next section. Now the electric potential is the work needed to bring a unit charge up from infinity. So if we have several charges, there might be some positive and some negative charges, and we're going to bring a certain charge by any path that we want to up to a certain position. Let's say we're going to bring it up to a position vector r, and this is a charge which is a charge q, which is unity. In other words, it's 1 coulomb. Then the amount of work that we have to do to bring that from infinity and bring it all the way up to this point is called the electric potential, V of r. And you'll notice that that is not that potential. The electric potential, V, is not a vector. And the potential energy is not a vector. Both of these are scalars, whereas the force and the electric field are both vectors. So V of r is a scalar, and it's measured in terms of volts, which is a coulomb, a joule per coulomb. It's the work you do per charge. That's the electric potential. So V, we're going to find, is the work that we do divided by the charge it takes to bring that in to a given position r. So it's going to be joules per coulomb. That's potential. Now this is something that you've seen before. In fact, you're familiar with volts, like the voltage on your car, the voltage for your AC, for light bulbs, and so forth. So that is called the potential, the electric potential. Now I can plot equipotential lines, and they're kind of like isotherms. If I have a positive charge here, then you know the electric field goes out in every direction. But an equipotential line goes around this charge at a fixed distance. Kind of like you could imagine this is a hill, and this is a path that neither goes up or down the hill. It's of equal potential in the same sense that we would have for gravity. It means you can walk on this line and not do any work. That's why we say it's an equipotential line. Now, these equipotential lines are like isotherms and isobars for the weather. We'd have another one here, another one here. They go all the way around. And if we have equal potential lines for positive and negative charges, then it becomes more complex, as we'll see. The contours are always exactly perpendicular to the electric field lines everywhere. You notice how I've drawn these, they're exactly perpendicular everywhere. And you note that the potential, like the electric field, exists at every point. You don't have to have a charge there. We have a potential right here, even though there's no charge there. Why? The potential right here is how much work we'd have to do to drag a positive unit charge, plus 1 coulomb, from infinity and drag it up to that point. The potential, therefore, is a property of the position, whether there's anything there or not. Now, E is equal to the negative of the gradient of that potential. That's a more complicated concept in vector calculus, but if I have these potential lines here, the electric field is the gradient of how much that is changing as I move perpendicular to them. The constant V curves are a good visualization of the electrostatic environment. And we can see that as I move around here, I've got the same electric field everywhere, along this line, and perpendicular to that are the electric fields. We always use changes in voltage rather than the absolute values. It really doesn't make much sense to talk about the absolute value of the voltage. We can look at what the voltage is relative to a point at infinity. But if we take something like a battery, we'll see it has a positive and a negative terminal. What we're really interested in is the work necessary to take 1 coulomb that's positive from one terminal to the other terminal of the battery. For a battery, that's going to be 12 volts. What you should do is convince yourself that the constant part of the potential is not observable. That's why you're only going to be dealing with changes in the potential V. And we'll see how that plays out in just a moment.